Dhanasega is working as a lecturer in Department of Information Technology, Anna University, Chennai. He finished his MCA from Urumu Dhanalakshmi College, Bharatidasan University. He finished his ME in Computer Science and Engineering from College of Engineering, Anna University. His areas of interest are multi-core programming and architecture, programming models, compiler, automata theory, cryptography, and algorithms. He is an expert in subjects like compiler design, formal languages and automata theory, analysis of algorithms. His research area is code generation for multi-core architecture.
Welcome to the UGC lecture series on computer science. We are studying the compiler design subject as far as these continuous episodes are concerned. Here we are that is studying the parsers, of which the SLR parsing table is the one which we are currently studying. The SLR is the most simplest one under the LR that is parsers category. So, which are actually the efficient parsers among all the parsers categories are concerned. So, as far as the previous episode is concerned, we have seen that is the construction of LR of 0 items, which is actually needed for the construction of SLR parsing table. So, actually the parsing table could be constructed by 3 methods. The first method is the SLR method. So, if you want to construct the LR parsing table by using the SLR method, we need the LR of 0 items, or in general we call it as items, which is actually obtained with the help of that is the augmented grammar, which is converted as obtained from the given context free grammar by introducing an additional production, which is nothing but the starting symbol dash derives start symbol, which is introduced for bringing the accept action into the parsing table of that is the LR parsers. So, once we have obtained the LR of 0 items, the next step is we need to compute the parsing table, or we have to generate the parsing table, and after constructing the parsing table, which is for the given grammar, we can go for parsing the string, that is any string, by using the parsing table. So, if you parse the string, and if the string is already there in the language of the given grammar for which the parsing table has been constructed, then we can say that the parsing that a tree, that is a derivation tree, will be generated as an outcome. And if you find that a parsing tree cannot be constructed, or if the string is not there in the language of the grammar, we will not be able to construct a parse tree. We fail to construct a parse tree, and we will produce appropriate errors which are mentioned or which are propagated as far as the parsing table are concerned. So, if the parser is not a error handling parser, then the entries are all empty as far as the parsing table is concerned. So, whenever we see an empty entry which says that the parser has detected some error on the input. So, that is what the idea behind the rest of the topics as far as the that is SLR parsing table construction is concerned. So, in the previous episode we have seen how the LR of 0 items are constructed for the expression grammar. I will go for a simple refresh on that part. From that we shall see that is how we are constructing the LR parsing table. So, here is the grammar. We have the expression grammar, that is E derives E plus T or T, T derives T star F or F, and F derives opening bracket E closing bracket or ID. And now we have got the that is augmented grammar by introducing the new production E dash derives E, and there are totally 7 number of rules, including the one which is introduced for converting the given grammar into its equivalent augmented grammar. And from that we have got the initial state, that is I naught, by applying the closure of E dash derives dot E. We are having that is 7 number of items in the state number I naught. Then from this we compute the various resulting states, that is state number I1 as a result of I0 comma transition for E, I0 comma transition for T gives you I2, then I3 is obtained for F, I4 is obtained for opening bracket and I5 is obtained for ID, and the remaining states are obtained as follows. That is, we are having I6, I7, I8, and we have there is I10, I9 here, I10 and I11. So, we have generated states from 0 to 11 as an outcome of the computation of LR of 0 items. So, there are totally 12 states generated for the given grammar, that is the expression grammar. Now, we shall see that is how we are making use of this LR of 0 items for the computation of the LR parsing table. So, we have a simple algorithm which will compute the SLR parsing table from the given LR of 0 items. So, how we are generating the SLR parsing table from the LR of 0 items is that is with the help of a algorithm. Here is the algorithm. So, as far as this algorithm is concerned, the input is going to be the canonical that is set of items. So, in the previous grammar, that is meant for expression grammar with no ambiguity, we got 12 number of states starting from I0 up to I11. So, by using all these 12 states, in each state we are having some set of items. We shall see how the parsing table has been generated by using this algorithm. So, the output is going to be a parsing table, that is SLR parsing table with two different components. One is the action, another one is going to be go to. So, what do we do here is, we are looking at the state number I, that is going to be the current state, and within which we find an item of the form, that is A derives alpha dot small a followed by beta. So, two actions can be that is filled in other than the accept action. One is going to be the that is shift, and another is going to be reduce. So, two rules are there. One is meant for how we are filling the shift action, and another one is how we are filling the reduce action. To fill the shift action, we will find items of the form A derives alpha dot A beta, and if it is in a state called I, then we have to find out after shifting this A onto the stack, where from we will continue the parsing process. That is what the question now. So, we have dot here, followed by that we have a small a which is a terminal. So, now we compute the transition function for the terminal a. So, where do we go, or where from we will resume the rest of the parsing process. So, we start with I, for the symbol a we go j here. So, go to of I comma a, if it is giving ij, the actual meaning of this that is transition is, from the state I, for the input symbol a we continue the parsing from j, but before that you do a shift action. So, that is what, if a derives alpha dot a beta is in I and go to of I comma a is equal to ij, then we fill the action of I comma a is equal to shift j. So, action of I comma a is equal to shift a is going to be the output, which will be used for filling the table which is nothing but the SLR parsing table. That is about a shift action. So, now to look at the reduce action. So, reducing is possible only if the dot is on the extreme rightmost end. So, if it is on the extreme rightmost end, if a derives alpha dot is an item which is there in the state called I, then if action of I comma a is equal to reduce of, we are setting reduce of a derives alpha. So, the question is where from you got this small a. So, we are looking for an item of the form a derives alpha dot, and we got it in state number I. Then if action of I comma a, we are setting the action of I comma a to reduce a derives alpha, but this a is the set of all symbols which are following capital A. So, for all a in follow of a. So, if a derives alpha dot is in I, then for all a in follow of a, set the action of I comma a as reduce a derives alpha. The third one is how will you fill up the that is accept action. So, if we have S dash derives S dot in some state called I, that is, this is the production which you have introduced for converting the given grammar into its equivalent augmented grammar. So, if S dash derives dot S dot is in the state called I, already I said that the reason why we are introducing this particular item, it is just for that is introducing the accept action into the table. So, if S dash derives S dot in I, then action of I comma dollar is set to accept. So, that is going to be the way in which we are that is introducing the accept action into the parsing table. So, three actions have been that is introduced into the parsing table. The first one is shift action, here is shift action, and the second one is the reduce action, here is the reduce action, the third one is going to be the accept action. So, all these three are introduced as part of the action component. So, when you complete this, we will find some of the entries in the parsing table, especially on the action component as empty. So, what do they all refer? They are all referring to the erroneous entities. So, if we have an error handling parser, even all these empty cells are going to be filled with appropriate error recovery routines or error reporting routines, so that we will not find out even a single cell as empty cell. But if this parsing table is going to be a conventional parsing table without any provision for that is error handling, these cells are empty, and if you are looking into those cells, automatically we will be reported with that is errors. The parser will not be able to continue further. So, now there is another component in our parsing table which is called the go to component. How the go to component will be filled? As far as the go to component is concerned, the states are row wise, actually this row wise indexed by state numbers and column wise indexed by variables. So, in this grammar that is which is actually meant for your that is expression grammar, we have only three variables E, T and F. So, we will be having three columns on the go to component, and all the states will be considered as rows. So, see the algorithm which is meant for constructing the go to. So, we are having the condition, that is if go to of I comma this capital A. The reason why we are having capital A is that is go to is going to be defined only for variables, not for terminals. So, go to of I a comma A, if it is going to I j, then you go for go to of I comma set, that is set go to of I comma A is equal to j. That means, if you go to ith state for the variable A and resume the parsing from j. The similar action actually already we have carried out as far as the shift action is concerned, but it is all meant for terminals, but if it is variable, this was the case. So, go to of I comma A is equal to j, provided we have already computed the go to function for I a comma A is equal to I j, and all the rest of the items are considered as errors, and the initial state of the parser is the state constructed from the item s dash derives dot s. So, in general it is going to be the first state of the canonical set of items, that is nothing but I naught. So, this is what the that is algorithm being used for constructing the that is parsing table. So, the input for this algorithm is LR of 0 items, and the output is going to be the parsing table for the given augmented grammar. With the two components, we will be having both action component and as well as the go to component. Action component is mentioned for all terminals from each state, and the go to component is defined for all variables from each state. So, we shall see that is how we are constructing the parsing table. So, there are 12 states available starting from 0 to 11, and two components, one is action, another one is going to be the go to. So, the action component is defined for all the terminals available in the grammar with an additional terminal called dollar denoting the end marker of any string. So, plus star opening bracket closing bracket id and dollar. The go to component is meant for three number of variables E, T and F. So now you can find out that the actions are here, there is S4, then R2, they are all available. So the S4, it means that shift the current symbol to the stack and resume the parsing process from the state number 4, that is the meaning of S4. And R2 means reduce by using the rule number 2. So we have numbers, the 4 says continue from 4th state and this 2 says reduce with the help of the rule number 2. So now we can see that is how these entries are filled. So to fill these entries, the input is going to be the canonical set of items, and from each state we will find out the items, and by applying the algorithm we will be able to fill these entries shift, reduce and as well as there is accept action. So we shall see how we are filling, but after a short break. Welcome back. We shall see that is how the entries available in your that is the parsing table are going to be filled with the help of the SLR parsing table construction algorithm. The input is going to be the set of all items. We have the state number I0 here, then I1, I2, I3, I4, I5 and all the remaining states are available here, I6, I7, I8 and then I9, I10 and I11. So totally 0 to 11, 12 states are available. So we are having 12 number of rows from 0 to 11. Let us see, that is going to be the first one, that is what happens as far as the state number I0 is concerned. We can say that we are actually looking for terminals from 0. The terminal is the opening bracket, another terminal is going to be ID. Remaining all the items are having only variables next to dot. So if you take f derives dot opening bracket e closing bracket, it is of the form a derives alpha dot a beta. That small a is nothing but this opening bracket here. So if you apply go to of I0 comma opening bracket, we go to the state number I4 here. So the action is now in the state number 0 for the terminal opening bracket, you shift the opening bracket onto the stack and continue from 4. So this is how we are filling the shift action. So we start with 0, that is in the row meant for 0th state, in the column meant for opening bracket, put the action shift and continue from state number 4. So that is what we are having, and that is S4 as far as the state number 0 is concerned. 0 for opening bracket we have S4, it is because of f derives dot opening bracket e closing bracket is in 0, go to of 0 comma opening bracket goes to 4, we are having S4 here. Similarly, if you look at the action for f derives ID, here also we have dot followed by a terminal. So f derives dot ID is in I0, from 0 for ID we go to state number I4, sorry I5. So the action is 0th state, column is ID, the output is shift ID onto the stack and resume the parsing process from 5. That is shift ID onto the stack and resume the parsing process from 5, which means S5 is the action. So we have 0 comma that is 5, it is going to be 0 comma ID, we will be having S5. So this is how we are filling the shift actions. You can see two more entries like 1 comma plus, how we are getting, that is S6. So we should go for the state number I1. So here we are having I1. We have a terminal here, that is next to dot we have a terminal here, the terminal is plus. So now state number I1 has an item of the form a derives alpha dot a beta, that is nothing but e derives e plus dot t, sorry e dot plus t, and now we have to find out what is going to be the outcome for go to of 1 comma plus. So, go to of 1 comma plus, it is going to 6. So, that is what we are having S6 there. So, in simple words, if you want to compute the shift actions, you find out all the go to functions which are meant for terminals. So, it is 1 comma plus is S6, 2 comma star is S7, then here it is 4 comma opening bracket is going to be S4, and 4 comma ID is S5, then 6 comma opening bracket is S4, 6 comma ID is S5, 7 comma opening bracket is once again S4, 7 comma ID is S5, 8 comma plus is I6, 9 comma star is I7. So, this is how we are obtaining all the shift actions. You can find up to that state number 8 for plus and for closing bracket. So, now we shall see that is how we are filling the reduce action. See, for the reduce action, what the algorithm says is you find out an item of the form A derives alpha dot. So, we have two cases here. One is in state number I2 we are having an item of the form E derives T dot. State number I3 we have an item of the form T derives F dot, and in state number 5 we have an item of the form F derives ID dot. But we have another item, that is E dash derives E dot, and that is E dot. It is a special case for which the accept action is going to be written onto the table. For all the remaining items of the form A derives alpha dot, so what should be done is, let us take the state number 2 here. So, we have that is E derives T dot. So, 2 is the state number. So, 2 comma, what are all the intersections we need to write the that is reduced by E derives T dot. That is, for all the follow symbols of E, so we should write E derives T dot into the parsing table for the reducing production. So, instead of writing the complete production, we write the production number which is meant for E derives T dot. So, E derives T dot is going to be second production as far as the list of productions are all concerned. So, you can find out 2 comma plus, 2 comma closing bracket, and 2 comma dollar. We have the entries reduce by using E derives T dot, reduce by using E derives T, and reduce by using E derives T. It is all because of the follow set of E includes plus, closing bracket, and dollar. Then when you go for the state number 3, we have an item of the form that is R4, that is T derives F dot. So, we have R4 here, R4 here, R4 here, and R4 here. It is all because of the follow set of T includes plus, star, closing bracket, and dollar. And similarly, we are having in 5 F derives ID dot. So, F derives ID is the sixth production. So, we are entering plus 5 comma plus, 5 comma star, 5 comma closing bracket, and 5 comma dollar with reducing production the sixth one. So, we are having R6, and in 9 we are having R1, that is E derives E plus T dot for plus, closing bracket, and dollar, because the close, that is follow set of closing bracket. So, follow set of E are plus star and dollar, sorry, plus closing bracket and dollar. Then we are having R3 here, T derives T star F dot, third production, and the follow set of T are plus, star, closing bracket, and dollar. So, we are having this entry, and finally it is going to be F derives open bracket E closing bracket, that is a production number 5, and we are having the entries for 11 comma plus, 11 comma star, 11 comma closing bracket, and 11 comma dollar. And 1 comma dollar is accept because E dash derives E dot is in the state number 1. So, now to fill up the go to entries available in your various columns indexed by the variables, we have to compute only the items of go tos which are defined for variables. So 0 comma e we are going with 1, then 0 comma t it is 2, 0 comma f it is 3. That is over as far as this page is concerned. And here we find that 4 comma e it is continue with 8, 4 comma t continue with 2, 4 comma f continue with 3, then 6 comma t continue with 9, 6 comma f continue with 3, 7 comma f continue with 10. That is all. So this is what the go to entries are all obtained from this LR of 0 items. So we have the last entry, that is going to be f, which is from the 7th state for the variable called that is f. So now we have the complete parsing table. So we have filled the action entries for various terminals and go to entries for the various variables, and the rest of the entries, that is the entries which are not yet filled, are considered as errors. So after completing the parsing table, after constructing the parsing table, we can go for that is the parsing of any string which is in the language of the given grammar. So we will be having a stack for the parsing process which will be maintaining the various terminals and variables along with the states, and there is another component called the buffer where the input will be initially loaded. The third column will be telling you that is what kind of action is being carried out in each stage of the parsing process. The stack is initialized with there is an entry called 0, which says that 0 is the first state where from you have to continue the that is start the that is parsing process, and the input is completely loaded with the entire string which is to be parsed, which is terminated by using a dollar, which is nothing but the end marker. And if it is going to be initial configuration, then we have to find out whether we should continue with the shift action or reduce action based on the current configuration which is obtained by using the stack and buffer. Here the initial configuration is 0 comma id, which says that shift 5 is the action. So shifting id and continue from 5, then 5 comma star, the action is going to be a reduce action, reduced by using f derives id. So what happens is, since the right hand side contains only one terminal, we are popping two symbols out of the stack. Those symbols are id and 5, and we will push the left hand side, so f will be pushed onto that. So now we consult what is there in 0 comma f in go to component. So 0 comma f says 3 in the table, so push 3 onto the table. So what happens here is, it is a reduce action, number of symbols on the right hand side is 1, so pop 2 symbols, 5 popped out, id popped out, push the left hand side, it is going to be f, and now consult 0 comma f in the go to table, which says that 3 is the integer, so push it back onto the stack, so you will be having 0 f 3. So now you consult 3 comma star. 3 comma star is also saying that there is a reduce action. So this time the production to be used for reduction is going to be t derives f. So once again we are having only one grammar symbol on the right hand side. If there is only one grammar symbol, two number of symbols are to be popped out. So f3 and f has gone and t will be pushed inside. 0 comma t says 2, and 2 comma star is going to be shifting star onto that. Then we are having id comma 5, for 5 plus its reduce action, this id will be replaced by that is f, so we will be having t star f. So what happens for t star f is going to be reduce action, because of star is taking more priority than the plus, so t star f gets reduced. So once t star f gets reduced, we will be having t here, so then it is going to be reduction by e derives t, and then we are having 0 e 1, but still we are having something else in the buffer, so continue the shifting or reducing, and if you are continuing like this, finally we will be having 0 e 1 with a dollar on the buffer. So we are consulting 1 comma dollar onto the table, the 1 comma dollar says accept. So that is what the final configuration. So whenever we see that 1 comma dollar, since 1 comma dollar is having accept action in the parsing table, we can say that the string which we have taken for this parsing, that is id star id plus id, is a valid string, and the parsing table has been used for constructing the parse tree. The parse tree construction is successful, so it is going to be an accept action. So, this is how the parsing has been that is done. So, to summarize, we have seen how the parsing table has been constructed, and then we have seen that is the how the parsing is to be done with the help of the parsing table, and the question components, and for which we will be asked to construct the SLR parsing table, and you will be given a string provided the SLR parsing table constructs the parsing table in a successful manner. That means, if the grammar is SLR, which implies that no duplication of entries into the parsing table. So, either you will be asked to there is construct the table, or you will be asked to construct the parsing else, do the parsing else, provided the table has no multiply defined entries. So, with this I complete this episode. Thank you all.